they're kind of nice. They're kind of a ubiquitous topic that just appears in lots of areas of math. And we'd like to study the symmetries of that algebra. So, we kind of already understand how to classify finite symmetries of an algebra. This is through group actions, right? If we have a group acting on algebra, we get a group homomorphism from G into aught A. Um, and what we can do is for each of those automorphisms, you can kind of create a bimodule, right? A bimodule where we have a left-right action of the algebra, where the left action is just left multiplication, and the right action we just twist by the automorphism and then multiply by that A1. And these bimodules kind of satisfy this property that if we take their relative tensor product, it's somehow like composing the automorphisms in some sense. Um, and so you can, in some ways, this is kind of like somehow a group action on an algebra induces some sort of association with each group element and some bimodule. Um, and so, unlike automorphisms, not all bimodules will be invertible, right? So an automorphism, right, it's an isomorphism, so it has an inverse. But you can kind of, through this example, you can kind of think of bimodules of an algebra as kind of like generalized, not, sometimes, or like non-invertible symmetries of that algebra. Um, and we can kind of study that through the category of bimodules over that algebra. We denote this category BIM-A. Um, the objects here are bimodules, and the morphisms are going to be some bimodule homomorphism, right? Um, but with this category, this is not the end of the structure. There's actually more structure on top of just objects and maps between them. So let's kind of dive into that a little bit. So given the category BIM-A, we have some like tensor product, right? We can take two bimodules, take their relative tensor product, and produce a new bimodule. This tensor product is associative, and there's a unit object that kind of, the algebra which acts as the unit in tensoring. So BIM-A, on top of it just being a category, has this structure kind of also living inside of it. We're going to define a monoidal category as a category with a map like a tensor product that is associative and has a unit object. And so BIM-A is kind of a really good example, a classic example of what we would call a monoidal category, right? It's a category with associative tensor product and with a unit. Now, if you were to go Google monoidal category and you're going to go read this, go Wikipedia this, you're going to see a lot more extra stuff being packed into there. And this is true, but like somehow um, to get the idea for now, just think of category with an associative tensor product and that has an associative unitary tensor product. Somehow gives enough of an idea for this talk where you can get the idea and think about the examples we're going to talk about. And then if you're motivated by this and you want to go learn monoidal category theory, yes, you have to go learn the category theory that makes this formalism work, but it's kind of redundant for now. Okay, so we're gonna spend this hour talking about fusion categories, which are like special types of monoidal categories. Um, and you can kind of think of fusion categories as like generalizing finite groups and their representation categories. These are kind of the nice examples here. And so, the question I propose is like, one, how can a fusion category act on an algebra, right? Somehow you have like a categorical dimension mismatch. You have a category acting on an algebra. This somehow doesn't match up properly, so you need to do something. And if fusion categories are what I claim they are, which is like a generalizations of finite groups and their representation categories, excuse me, do these fusion category actions in algebras generalize just regular group actions? Um, you know, Obviously, I'm giving this talk right now, so the answer is yes. But we'll see kind of over the next chunk of time, like why, right? That's gonna be kind of the question, or why? How do we kind of make this equivalence, go back and forth? So. let's kind of build slowly kind of the first example of a fusion category. Um, and so if we let G be a finite group, here I need this category to be semi-simple, so just assume the field is C, or like as long as the group doesn't divide the characteristic of the field. Um, right, we all know this category of representations over a group G, right? There's objects are vector spaces paired with maps, um, where we have objects are representations, and morphisms are these like uh, intertwine representation intertwiners that intertwine the action of G on the vector space. Um, Now, this is not, if you've studied, your graduate algebra course, this is not, once again, this is not all the structure that representations of G have. There's more lying underneath, and we're going to kind of slowly but surely break that down and then use this to motivate what the definition of a fusion category. So, rep G has like these following properties and structures. One, it's a K-linear category. So that means that the Hom spaces between any two objects are going to be vector spaces, and their composition is bilinear. Um, It's finally semi-simple, right? We have Maschke's theorem that tells us that every representation will break down into a direct sum of irreducibles up to isomorphism. And we can kind of figure out what the simple objects are because their endomorphisms are the ground field. We have an associative tensor product, right? We can take two representations, take their tensor product, or take three, and then the ordering in which we tensor them up to isomorphism doesn't matter. We have a simple unit such that when we tensor it with a representation, nothing happens, or up to isomorphism, nothing happens. And for each representation, we have a dual representation, right? We have this kind of, you can take the dual vector space and define the dual representation over the dual vector space, such that we have these kind of canonical evaluation and co-evaluation morphisms satisfying the usual duality equations. So this is kind of rep G, and now we're going to look at what a fusion category is. It is a K-linear category, right? That means that for any objects x and y, Hom x, y, the Homs between x and y are vector space, and their composition is bilinear. It's finally semi-simple, right? Every every object decomposes into a direct sum of simples, and you can figure out which objects are simple because they are the objects whose, you know, endomorphisms are the ground field. We have a tensor product that's associative and has a unit. And for each object, we have a dual object, satisfying the same duality equations that you would have for vector spaces. So when I say the word fusion category, um, kind of the first non-trivial example you can think about is think about rep G, right? Think about group representations. This is kind of an example that most people know and most people have worked with or encountered. And kind of we'll see in a second that it doesn't capture all of fusion category theory, but it gives you kind of enough to understand what I'm talking about. So if I write down a fusion category C in some theorem later on and you don't know you're confused, just think rep G. So, kind of I've defined this thing. Why should we care? Why should we study this? Why should we think about it? Um, and so, the idea is that fusion categories generalize the category of finite dimensional vector spaces with tensor product. There's important connections between fusion categories and representation theory, low-dimensional topology, and subfactors. Um, and if you're interested in mathematical physics, you can kind of use fusion categories in models to, these kind of particle models for quantum physics. Um, for example, my advisor and a bunch of other people are currently working on like building quantum computers out of fusion categories and uh, using models to come from fusion categories to build quantum computers, stuff like this. So these are kind of, for me, good enough motivations to why we should study them. Okay, so some examples. Kind of these three examples on the page are kind of the three canonical examples. Obviously, rep G, uh, finite dimensional vector spaces is another example. Right, every vector space can be written as direct sum of the ground field. You can tensor them. It's associative. It's got a unit. There's duals, stuff like this. And kind of another canonical example is the category of G-graded vector spaces or finite dimensional G-graded vector spaces. Here are the objects. You can think of these objects as lists of vector spaces, each vector space indexed by some group element. And then if you take the tensor product of those, you just take the tensor product like you would in vector spaces, but you kind of also multiply the group indexing. Um, these are kind of like I said, these are the three classical examples. They kind of give you enough tools to kind of get an idea of most things that are going on. Also, they have kind of a natural notion of dimension coming from the dimension of the tensor product of the vector space, right? All these objects you can think of them as just vector spaces in some sense. So there is a dimension that is associated with that, and that dimension will be compatible with the tensor product, right? Whether you tensor first, the tensor product of V tensor W has dimension of V times dimension W. Now, not all fusion categories kind of here's where we get interesting, right? This is somehow the last couple of the examples on the last page are all kind of things that people study pretty frequently. Not all fusion categories can be just understood in terms of just vector spaces. Um, the fusion category fib, this is called the Fibonacci category, has two simple objects, one in tau, that satisfy these fusion rules. Obviously, one tensors with one trivially and one tensors with tau trivially, but tau tensor tau is going to be isomorphic to the unit plus tau. And if you were to think of giving tau a dimension, because we're kind of trying to generalize representation categories, then you'd have that d squared is equal to d plus 1. And if you solve this quadratic, you find that the one of the roots here is 1 plus root 5 over 2, which is irrational. And your first thought, if you were just thinking just vector spaces, right, this is impossible, right? We can't have a irrational dimensional vector space. We all have everything's integer dimension. So, what is kind of going on here? Um, this is an example of a fusion category that's indexed by primes called PSU2 at depth p minus 2. Kind of the way you create these fusion categories, if you're curious, is you take it's like semi-simplifications of quantum group representation categories. These fusion categories have simple objects dx2j, and their dimensions are these ratios of sign functions. Notice that this is only an integer when j is equal to 0, because in that case the unit is x0 is the unit and the dimension is 1. And they satisfy these like complicated fusion rules that allow you to just show how you multiply them. Basically, what I'm saying here is dx2j tensor dx2i is this n here is the number of time, like the number of these copies in the decomposition of the tensor product into simples. And these n satisfy this, this equation here. So we should think of these things kind of in some ways as fusion categories are representation categories, but somehow they go beyond. Like you have abstract fusion categories. You can kind of think of this like for groups, you have, abelian groups, which we really, we like abelian groups, we study them, but they're kind of pretty well understood. And then you go to non-abelian groups and things get more challenging. The fusion categories that come from rep G and eventually rep H for a semi-simple Hopf algebra, these are pretty well studied and pretty well known. But once you leave that kind of space and go to just, arbitrary fusion categories or abstract fusion categories, these kind of become much more interesting and juicy because they're a lot more complicated. So to kind of
Sorry,
compare
just a question about your
yes,
previous slide.
yes,
So this is saying that the tensor product of any two objects has decomposes as a direct sum of simples, and the simples appear with multiplicity at most 1.
yes. This
Is
is
that
this is a
correct?
multiplicity. Yeah, every simple appears with a multiplicity 1 if it appears, right? It's not necessarily true that it
Right.
will.
If it appears, it has multiplicity 1. So is that in some sense like a the formation of the representation theory of SL2, where you have like a
So
similar.
I forget what quantum, so basically what the way you construct these, and I'm not like a quantum group expert. I just I need this is a nice fusion category to work with, and we'll see so why later. Is the like you take some quantum group at some of some you take the representation category of some quantum group, and then you're going to like you can it's one of these things where you like chop off everything after a certain point and like semi-simplify it down, and then that's now that's now a multi-fusion category. But the way to get like a fusion category here, or maybe it's a multi, I forget exactly what, but you need but I even restrict even further. I'm only taking the even representations of that semi-simplification. Um, right. So if you notice how all of these are indexed
Ah,
by two,
yes, all the indices are two.
I'm not. I'm only so like I semi-simplify, so I chop off like everything after a certain point, and then I'm only taking the even ones, and those even ones are the way we get a fusion category here. Or we get this specific fusion category, this specific family.
Okay, thank you.
Hmm. So where was I? To kind of compare and contrast, right? We kind of have the top bullet, we have rep G and vec G. These are the kind of things we know already and we understand pretty well. The dimensions of the objects here are integers. The associator, like the associator being the thing that swaps the parentheses for associativity, is like just the one from vector space. It's somehow like a trivial isomorphism where we just literally move the parentheses over. And you can think of these as like the objects as legitimately just being vector spaces with some extra structure. And the morphisms are going to be just linear maps that satisfy some properties. Now, for PSU2, we have irrational dimensions. Um, the associators in these categories are like there's still isomorphisms between the different ways you can parenthesize. Excuse me. But they're highly non-trivial. Like they're not like to write it down takes a tremendous amount of effort. And because these are not irrational dimension, you really can't think of them. I'm going to lie slightly and say you really can't think of them as like vector spaces on the nose, um, because right, it doesn't make sense to associate an object here with a vector space. But the objects you can think of them as kind of like points, and the arrows, the morphisms just can be arrows between these points. And so somehow the top example is the ones that you kind of expect to be fusion categories and are nice to work with, and somehow a lot of the juicy, interesting fusion category theory comes from these kind of abstract ones that aren't rep G or vec G.
Alex,
Yes.
h- uh, how can you like measure how trivial or non-trivial an associator is?
Okay, so it's more or less like there's two things. One, if your category is like equivalent, so if your fusion category has a fiber functor, whatever this means, like it somehow it maps a functor into vector spaces, it's equivalent to a representation of a Hopf algebra.
Yes.
Those ones will all have all the associators there are just the parentheses swap. So like V tensor W
Yes.
tensor U, you just swap the parentheses and don't change anything, right? Because they're all coming from vector space and we know how to reassociate in vector spaces. In I would say the way you can see the more challenging ones is when you're doing this, you're actually like I'm kind of somehow sweeping some of the category theory under the rug here, but like the associator, it's not just an isomorphism, it's a natural isomorphism that satisfies some bigger diagram, right? The pentagon equation.
Mm-hmm.
And going around the pentagon for like fib, like Fibonacci category, doing that pentagon, like if you go through and compute what the associator needs to be, so like you can do this. It's a linear algebra exercise. Like you go around the pentagon, you see what you get a system of a bunch of equations, you solve that equation, and basically like for those categories, like for example, the Fibonacci category, its associator is represented by like a scalar and a 2 by 2 matrix, and that 2 by 2 matrix has a bunch of like golden ratios in it and stuff like this.
Mm.
Um, and so when I say it's non-trivial, it's like somehow it's not just the obvious parentheses swap, and it also takes a lot of work to figure out. I remember I did this exercise like 3 years ago as a second year
Mhm.
PhD student. It took me like a whole week or so of like going around this pentagon equation and seeing like what coefficients popped out, and then getting a whole big system of equations and then trying to solve it. Does
Mm.
that answer your question?
Yes, yes, yes. Thank you.
Good. Okay. And so kind of, now we're gonna kind of transition to kind of building math between monodal categories, right? So remember, fusion categories were specific examples of monodal categories. And so we can kind of start to understand how, if we have two monodal categories, what should be the map between them. Um, and so for, if you can think of H as a semi-simple Hopf algebra here, if you know that, what that means, or think of H as a group, totally fine either way. Uh, there is a forgetful functor that takes a representation, v pi, and just chops the representation off, right? You had a vector space there, map the representation to that vector space. Notice that this kind of this kind of functor doesn't care which way we do things. We can either take the tensor product of two representations and then forget the representations, or we can forget, the two representations and then take their tensor product. Um, and so this is kind of what we call an example of a monoidal functor. It's somehow a functor that preserves the tensor product between two monoidal categories. Um, so let me kind of formally define it. If we have two monoidal categories, a monoidal functor. So here's this kind of I'm not sure how, like if you work in fusion category theory or just kind of category theory in general, you have this kind of like structure versus property conundrum where like when I say I'm a functor, it's not just a functor with with the property that that equation on the last page was true. To define a functor, I have to like pick out, I have to specifically say this is my natural isomorphism. So it's a pair, Fj, where F is a functor, and J is this natural isomorphism from these two, whether we tensor, we map and then tensor, or we tensor and then map, these are naturally isomorphic via that functor J, and we need to also send one to one. You can kind of think of these in some sense of being like a monoid, like, categorifying a monoid homomorphism, right? Monoidal category is is kind of in some ways a categorification of a monoid. So what is a monoid homomorphism? You send one to one, and you kind of are compatible with multiplication. So same idea here. This map also gives us a way to kind of act rep G on finite dimensional vector spaces. How do we do that? Well, we just take the representation, chop off the representation, and then just take the tensor product of these two objects. This will give us a new object in vector spaces. More generally, you can apply this for any subgroup of G where you just restrict the representation, and then you can kind of somehow use that to act rep G on rep H. And this is kind of building like modules over our fusion category. So what is a module category? A left module category of a fusion category is we have some category equipped with some bifunctor, some like map that kind of satisfies the usual module relationship of either you multiply in the, if you're over a ring, you multiply in the ring and then you act, or you act twice, right? Somehow these are the same. And here for a module category, we're going to have the same idea. The only difference being that like when you soup everything up to category land, you have to one, do things up to isomorphism. So this is why natural isomorphism pops out. Also, these things need to satisfy some like commutative diagram stuff that I'm kind of pushing under the table. But go if you decide to study this at any point, you'll have to like learn a little bit of this kind of category theory formalism. Um, and so similar to how if you can think of representations as group actions or group homomorphisms, you can think of a C module structure as either a category acting or a monodal functor into the endo functors of them. Right? This is kind of that same relation bumped up again for categories. One last category theory definition is that if we have two C module categories, we can define a C module endo functor. This is kind of just a C module functor. This is going to be a functor that does what you expect a module functor to do, right? You would like it to be compatible with whether you multiply and then map, act and then map, or act them or map then act, right? Once again, up to natural isomorphism, satisfying some coherences. And it turns out that like if we have the category of C module endofunctors will be depending on what kind of module category you have, will be at least a monodal category, sometimes a fusion category. Um, in particular, if we look at the C mod, so given that rep G is a vec is a rep G module category, the C module endofunctors of this example is this category vec G. Kind of tying the two group categories together in some kind of a natural way. So now we kind of have put down enough laid down enough groundwork to say what fusion category actions are and kind of start to understand what we're doing. And an action of a fusion category, right? The kind of the original question was, well, how can a category act on algebra? This is kind of somehow not doesn't make sense, right? You see the category is like somehow one level higher than an algebra, right? An algebra is an object in a category, but how do you act on these things? The way you do this is you kind of bump up the algebra to how do you create a category from the algebra? You look at its category of modules. And so an action of a fusion category is a C module structure on the modules over that algebra. This is equivalent to by some theory, there's a paper written in like 1960 by Eilenberg and Watts separately. This is equivalent to a monodal functor from C into BIM-A. And then so, I'm posing this question from like an algebraic perspective. Like my advisor and a lot of like his collaborators work on this problem in like a C star category, C star algebra perspective, where they're doing this to prove a bunch of theorems and analysis in operator algebra theory. I, you know, I don't know a ton of operator algebra theory, so I just delete the C star part, and I think this is a reasonable and interesting question to ask algebraically, like when, you know, do fusion category actions generalize group actions, and how can I act fusion categories in algebras? Because for me, algebras are inherently interesting because they just appear everywhere in mathematics. Okay, so now I want to talk about the kind of actions that we looked at the very beginning, right? So I was able to, I talked about how if you had a group action, you can kind of create these bimodules that kind of capture the group action in some canonical way. And really what we were doing is that if you were given an action of G on A, you can then produce a monodal functor from vec G into BIM-A that sends the simple G-graded vector space to a tensor that vector space. The left multiplication will be just defined by multiplication of NA, and the right multiplication, what you will do is you use the fact that secretly, sorry, this is supposed to be a subscript here. This is case subscript G. You secretly are, somehow KG is a Hopf algebra, so you can co-multiply out. Or just think of it as if you don't know what that is, think of action by B on the right. The only way it can pass is you would need to kind of multiply by G onto B. And this is the example from slide one, right? This is somehow building a bimodule indexed by your group elements such that they tensor product in a way that is compatible with the group structure. This specific action has more structure than a fusion category action. We kind of have these base spaces, the unit in the algebra tensor Kg, which are preserved by our morphisms and our associator. And kind of what I want to do is I want to capture that extra structure. And maybe eventually figure out what about the extra structure, if I can go back, what do I need to do to say, when are fusion category actions actually group actions? So we define a base action of CNA is defined by a triple where we have a monodal functor, right? This is just the definition of an action of a fusion category in algebra. But what we're doing is we're picking out a finite dimensional subspace for each one of these bimodules, such that like morphisms preserve that subspace, and the unit in the algebra is contained in the V1 subspace. Right? This is a monodal functor, so it's going to send the unit in C to the unit in BIM-A. The unit in BIM-A is just the algebra, and I'm requiring that we have some finite dimensional subspace of the algebra V1. I want the unit in the algebra to live inside that algebra, inside that subspace. Um, this implies that we have some like these subspaces tensor product, pretty nicely with Vx tensor over A Vy is as more to Vx tensor Y. Also, because basically you can work this out pretty easily that Vx will span a left-right projective basis of the bimodule. Um,
Sorry, what is a
Sorry.
projective basis?
so
Yeah, what that means.
a projective basis. Okay, a obviously a basis in vector spaces is like it's kind of a generalization of this, right? If you have a um, finitely generated projective module, then you have this is a direct summand of a free module. Like it's a direct summand of like it fits into some direct summand of a to the n. Um, and what this means is that like you can write so it's like a weakening of a basis for a vector space. Right? You can write every element in the bimodule as a linear combination of these basis elements times elements in the algebra. And it's not like a basis in a vector space where it's like, oh, they all have the same dimension and it's like canonical or something. There's like different ways to, it's there's a bunch of them and they're not all necessarily related. And they, you could have a projective basis with five elements and a projective basis with three elements, and they're not, but it's the existence of one, basically it's equivalent to saying that this bimodule will be finally generated projective as both a left and a right module. Um, right, you get this like mapping into the free module, and this gives you a finally generated like a some sort of projective basis for this bimodule, or as a left-right module. Does that clarify?
So in particular, fx is going to be uh, projective.
No, so the word projective basis, it's coming from the fact that the as a left and right module, it is a finally generated projective left and right module.
It would be free, right? Not necessarily. I
Sorry,
mean,
what's the question?
would it be a free module as a right or a left module? No, not
It's not
necessarily.
quite a free module but it's a direct summand of a free module, right? To be
Right.
finally generated projective is you're a direct summand of a free.
Yeah, of course. But so you're taking this, I mean, sorry to go into this detail, but so you're taking this projective basis, and for each one, you're taking all the actions that has with A, right? And then it's like a basis in the term, instead of having like scalars, you have elements of A to define this sum,
Yes,
or
yes. So I'm saying that as a like every
right,
element in the bimodule can be written as a direct sum of these projective basis elements times like it's like V1 A1 plus V2 A2 plus V3 A3.
right, yeah,
It kind of is like because when you're finally generated projective, you are a direct summand of a free module. You kind of get this weakening of like if you're in algebra A and the module's A at the end, there's a very clear basis, right? It's like you have this one, basically directs a bunch of ones
one, yeah,
lined up, and you can just choose whatever A times you want on the right.
right.
But when you're finally generated projective, you don't have that exactly, but since you can embed into the free module, you can build what we call a projective basis, which is like it's like you should think of it as like a
Yeah, you
weakened
take
version.
right, and these elements would be sort of idempotents that some are summands of the one, right? I mean, it's like one you can write it
Depends on
as
the algebra, right? Not all algebras. Like this is just defined over any algebra, right? So if I chose the polynomial ring,
right.
the only
Ah, okay, yeah, of
idempotents
course.
are just 0 and 1. In the path algebra, yeah, I'm gonna like the examples if we're getting to the path algebra eventually, the examples I'm interested in studying here are kind of like the ones that are
Yeah,
uh
projected.
projectives, like the canonical vertex projections.
The yeah, the
Also,
EIs for
Javier,
varieties
how much
system.
time do I have? Is it till 9:15? I don't know when the seminar ends.
Yes, I mean until because I don't know. Yes, 20 more minutes.
Okay, I just want to make sure I don't go over because then I don't want to take up everyone's day.
Okay, okay.
Okay, so if we have a based action, kind of you have this induced functor f prime that basically sends x to that subspace Vx. And a based action kind of over a functor is when this f prime is isomorphic to G. And we, one more important definition we'll use later, excuse me, is that we define a base action to be over a functor if, we define a base action to be separable if this V1 space is a semi-simple algebra of A, or subalgebra of A. By category theory, V1 will always be a subalgebra of A, but we would like it to be a semi-simple subalgebra of A. Now, we kind of looked at this example already, where if a group acts on algebra, we can produce these a separable base action where the base spaces here are like these 1 sub A tensor KG. But here, if we actually look at the f prime function, that one that kind of sends x to Vx, it's just this forgetful functor we've been working with. I've been kind of using it as a running example. And so if G acts on A, we produce a based action of vec G on A over this forgetful functor Fg. And kind of the theorem here is that based actions of vec G on A over Fg up to a natural equivalence, this is like basically some categorical data, are in bijection with G actions on A. So you can really think of group actions being vec G actions with some little extra structure on here. And kind of the proof that the idea for the proof is just reverse the idea to go the one way. And that, if you read my paper on this on the archive, you will read that this theorem is true for semi-simple Hall algebras. I did this in more generality, but I think groups are everyone knows groups and likes groups, so it's a kind of a good way to kind of present this material, but it will be true for semi-simple Hall algebras as well, where you replace this with co-rep H, and you replace this with the forgetful functor from co-rep H to vec. Okay, so that kind of motivates why we should care about these actions. What I want to do now is kind of go on to the path algebra, right? This is I have about maybe 15 minutes left, 20 minutes left, and I want to kind of get to the main part of the work I did. So I want to study separable based actions of fusion categories in the path algebra. Just as a quick reminder, right, you're given some multigraph equivalent, you can define the path algebra as it's the algebra whose base is the set of all path lengths, and the product is just concatenation of paths. And then, this graph has finite vertices. It will be a unitary algebra where the unit is just the sum of the vertices. For one quick example, just take this algebra that says, two vertices A and B, and we have an edge alpha from A to B and an edge beta from B to A. And this will be infinite dimensional algebra generated by alpha and beta, right? You can take alpha, beta, alpha, beta, alpha, beta, alpha, beta, alpha, beta, and this will be a new basis element. So you can do this forever and ever. And this will give you a, infinite dimensional algebra. Here the unit will just be A plus B, right? The sum of the two vertices. So not too bad. Why study the path algebra? Why this one? The absolute dream, of this kind of program, is that all finite dimensional algebras are Maria equivalent to quotients of the path algebra. Maria equivalent just means that they have the same representation categories or module categories. And so the dream here is we'll see in a minute, produced a bunch of monodal functors into the path algebra or bimodules of the path algebra. If I can figure out when these descend to the quotients, then you start to build actions of fusion categories on all associative algebras up to Maria equivalence, or all finite dimensional associative algebras. As we were talking about in the beginning, also just from there's people who are very interested in the path algebra and its modules for combinatorial perspectives. Modules of the path algebra are kind of closely tied to representation theory of quivers. So it has both an algebraic motivation of if you understand the path algebra and its quotients, you kind of understand all finite dimensional algebras up to some equivalence, and there's some combinatorial motivation as well. So what I want to kind of do is set the scene of what's already been done and kind of put this all into context of in 2021, Pavel Etnov, who's a very, very famous mathematician in my mind, maybe in my field. I'm not sure if he carries over to everyone else's field, but I know he's involved in a lot of different fields, so probably. Pavel Etnov, Ryan Kinzer, and Chelsea Walton built great actions of groups if you read their paper, they will say semi-simple Hopf algebras, but you can think of a group as a semi-simple Hopf algebra. On path algebras, using objects internal to a fusion category called tensor algebras. These actions were classified by a semi-simple C module category and a C module endofunctor. And so kind of, you read this paper and I have this theorem about like when group actions are fusion category actions and how to go back and forth. If you could classify some semi-simple Hopf algebra actions by this kind of data, when, if they're classified this data, what about fusion category actions? They should probably be classified by this data as well, right? Because they're somehow very similar. So that was already done. What I was able to show is that filtered actions of fusion categories and path algebras are graded, and a graded based action of fusion category and a path algebra up to some natural equivalence is classified by a C module structure on the vertices and a C module endofunctor. So this was not super surprising of a result, right? We already had people who had studied semi-simple Hopf algebra actions on fusion categories, and so fusion categories kind of generalizing this idea meant that this is probably going to be true in some different, maybe different level of categorical equivalence, but like would be true. Like the hard work I was able to do, or maybe the interesting work, is I was able to for the specific fusion category PSU2, I was actually able to classify all of the separable actions of fusion categories on the path algebra. And so this is my main theorem. You're going to read this and you're going to say this is kind of the duality of doing category theory, of like you can look at some really cool ideas and stuff like that, but sometimes when you write things up to certain categorical equivalences, you get super messy looking theorems. So this is like the kind of the way you should think about this is that really what that statement is saying is that all of my idempotent split actions of PSU2 on the path algebra, idempotent split means that the kind of exactly what the question was earlier, of like my V1 space here is the canonical vertex projections, right? It's this gives you an algebra of this gives you the algebra K, the size of number of vertices, and you can when it's that space exactly, you can classify the actions of PSU2 on path algebras as exactly by a C module category structure, a C module category on the vertices, and a C module endofunctor kind of representing the graph. And kind of the corollary is that all several base actions of PSU2 on KQ are in fact going to be graded. Okay, and kind of once again putting this kind of in, kind of giving you some idea of why this works or why this is interesting. It is the fact that I prove this is not proven by like Yoneda lemma or some overarching category theory statement that like you just kind of push it through some category nonsense and you get out the result you want. This theorem ends up being true by like a bunch of algebraic number theory, and the fact that the only module category over PSU2, or the only indecomposable semi-simple one, is itself. And so I was able to reduce this kind of problem to like looking at matrices under conjugation and then looking at like their eigenvalues and eigenvectors. And for these fusion categories, PSU2, there's a kind of a matrix called the S matrix that kind of helps you it kind of diagonalizes all these things and kind of tells you what the eigenvalues and eigenvectors would be. But then to actually, if you read my it's like 30 pages of category theory and then the last 15 pages are a bunch of algebraic number theory, it's interesting and fun. Like it's interesting and unique that like the reason why this is true is not some like category theory abstract nonsense, but I had to get my hands quite dirty and like really work through like learn cyclotomic ring theory to figure out this result. And so kind of to explain what this result is actually saying is that like the only graphs that the Fibonacci category, remember, is an example of PSU2 is PSU2-3. The only graphs that of two vertices that the Fibonacci category can act on here are like graphs that look like this, where we have two vertices, we have m paths from A to B, m paths from B to A, n paths from A to A, and n plus m paths from B to B. There was kind of the Fibonacci kind of thing going on here, n, m, n plus m. Um, and you can generalize this idea up to PSU2 can act on graphs with 2K vertices that kind of have this structure appearing everywhere almost. Where like if you had like groups, 4 vertices, you'd have to have you partition them into sets of two, and then the paths from each of these kind of subgraphs look like this, and the paths from one partition to the other partition look like this as well. Um, and so this kind of is really explicit, right? But what I was able to show is that these actions all kind of have to follow this kind of structure for PSU2 at depth p minus 2. And so kind of the follow-up question is like, are all based actions of fusion categories on KQ graded, right? I was able to show for PSU2 that yes, they are in fact all graded. And your next question is like, well, is it just true for any, is somehow any fusion category action on the path algebra going to be graded? The answer to this is like pretty quickly no, just because then otherwise all group actions would have to be graded in some sense. And you can kind of quickly construct a group homomorphism or sorry, a group action that doesn't preserve the grading, and that will induce a base action that also doesn't preserve the grading. And so this is kind of a good self-check of like that there is interesting things happening here, and it's not that just all fusion category actions are great, and somehow that work by Chelsea, Walden, Pavlet, Novin, Ryan, Kinzer kind of did everything already. No, like there's still a lot to do because we understand very little outside of PSU2 about the non-grade actions of fusion categories on path algebras. Okay, so that was it. Thank you all for listening. Um,
Thank you.
well, I made it a 50-minute talk, so I wasn't sure if it was 50 or an hour, but I think I'm right on 50 as well.
Oh, yes. I don't remember which time we started, but it was more or less like 50. Yes. Great. So, do we have any questions?
Yes. Um, well, I have a bunch of questions actually, but right. So the examples that in these other papers I mentioned before your talk are quite different. I mean, um, they tend to be finite dimensional, right? But then apparently then the fusion category would not act on the algebra itself, but mostly on the module category, I would guess. Because if you take like the bipartite A4, you're aware with this figure?
I am not. So,
Can I try
what
to
paper are we
draw it?
referring to here?
So the paper by Edmund Heng and
Okay, this one. Okay.
Ben Elias. So the idea is that you would get some quiver which has exactly 4 vertices, right?
Mm-hmm.
And these 4 vertices have so you number 1 to 4, and you have 2 arrows going from 1 arrow going from 2 to 1, and 1 arrow from 2 to 3, and only 1 arrow going from 4 to 3. Let's say.
Yeah.
Right. So in a way, this is A4 and it has very nice properties, but then there is an action on the module category of those guys and the representations of these guys, which are finite dimensional, and they seem to be quite far away from what you're doing, right? In a way.
Yeah, so I mean, for almost all the examples that I was able to concoct, all the path algebras that I can act on are like infinite dimensional path algebras. They all are like have some cycle going on somewhere.
Right. Yeah.
Um,
And where does this cycle come from? Do you
I
can
mean,
explain this?
so in some ways, it's coming from like basically what like this graph is really a graph built out of the fusion category.
Okay.
Like this is not like a like somehow like the only graphs that that fusion categories act on in a graded way are somehow graphs that are really just coming from the fusion category. Where like you can think of if fib is a modular category over itself, you have two simple objects. You identify each of those simple objects with the vertices, and then the action of tensoring by objects in fib kind of gives you this graph, more or less.
Right.
Like
Yeah.
you can really think of like n and m as like this is the number of one, like this is the number of ones, and this is the number of taus or non-trivial elements, and that they satisfy this kind of.
Right.
And
Yeah.
so
Yeah. Yeah.
more or less the fact that fusion categories all have like there's like a theorem that someone proved in fusion. I think it's my guess is it's some out of either Pavletnov, Viktor Ostrich, Dmitry, or one of these people who kind of found the field. Um, is that like eventually if you tensor x with itself a number of a set amount of times, you will always get back to the unit, and you kind of get these like loops of like x to the n, x tensor x tensor x tensor x eventually has one in it, but then you tensor with another x and you get back to x, and so you have these like loops. You kind of guaranteed to have loops in some ways. If
Right.
if we're building
But
if you can believe that we're building these actions out of data internal to the fusion category in some way.
right. Yeah. 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 But this one is a direct summon only of
Yeah,
that
if you were to
big
like
tensors.
yeah, I mean if you were to like but this is the graph. If you want to like compose the graph, you would like you can kind of think of it as like tensoring in some way. So like
Yeah.
if your graph was if you let's say n was 0 and m was 1, this is like represented by just the um element tau in fib. Tau tensor tau is 1 plus tau, and you kind of would, kind of the paths of length 2 are kind of represented by 1 n tau.
Right.
And then to get the path of length 3, you tensor with tau again, and tensor with tau, and so on and so forth. You keep kind of adding all the paths of length 1 again, 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 and somehow those are represented by whatever the quiver is looking like.
Yeah.
So in this case, is it something like the category of endomorphisms of fib sort of contains all copies of this for arbitrary n and m, and you're just plucking out like a specific
Yeah,
direct
so
summand
so
in
the
there?
way you can think about this is for a semi-simple there's a paper on I think it's called Fusion Quivers by I forget this it's on the archive in like 2023. I forget the author. It's but like the way you can kind of or this is just generally I think well known, it's written down there, but you can think of if you have a functor on a semi-simple category, an endofunctor, you can associate that with a quiver, right? If you just like you have x1 gets mapped to x2 plus x3, just the x1 vertice has arrows going to x2 and x3. And kind of, fusion categories are semi-simple categories. And so like the action of a fusion category on a semi-simple module category gives you a quiver in some sense. And this is kind of how we're producing these things, is we're like looking at you kind of you do some theory to kind of show that uh, these kinds of actions of fusion categories are classified by a C module category and a C module endofunctor. And then, in these specific cases where it's graded and stuff like this, you should, 'cause somehow the endofunctor needs to kind of be internal to the fusion category, giving you some quiver from it.
Wow. So, do you have any more questions?
I had a question as well.
Great.
Thank you, Alex, for the nice talk, by the way. I will need you to show me the main theorem that you had again, that I did not have time to read through the second half of
It's
the
it's
statement.
okay. I mean, I state my main theorem because my main result because this is the thing I proved, but
Mm,
objectively, like it's quite because of like I classified these actions up to monodal natural isomorphism, which is a very fine level of equivalence.
mhm,
And that's great that I could do it. The downside is that like it makes my theorem somehow inherently messier than like I really wanted to capture. Uh,
mm,
like if you do this, like if I, you can prove this up to like Morita equivalence or something, and this is kind of what this is saying here is like really this data, this big partitions of the vertices is really C module category and C module and the functor. But like if you're choosing a C module category, you have to like pick an assignment of the semi-simple objects in that category with the different module category, like the different objects in your module category. And like different swapping those can kind of create different actions up to they wouldn't be monodally natural isomorphic as functors. And so this is why all this bijection stuff pops up. Is that
Hmm.
like this is really me choosing a module category structure. And then with is like kind of picking a basis here for all the different module categories. And then once you pick a basis, then these subquivers kind of get decided by that choice of basis in some way.
Hmm.
Um,
So yeah. So okay, so you're grouping your vertices into kind of sets of the same size and
yeah, so for
stuff like this.
PSU2, there's this, it's the fact that the only indecomposable module category is itself. And so all semi-simple module categories are just direct sums of PSU2 a bunch of times.
Hmm.
And so like really this is why this is really nice to work with is that for like let's say like we take rep S3. Rep S3 has three irreducible module categories. Or has at least it has more than three. Sorry, it's more than three, but like it has multiple ones. You have rep S3 is a module category of itself. You can restrict down to rep A3. That's a module category. You have rep Z2 because you can act on that subgroup. You also have the map into vec. And so if you wanted to build, let's say you wanted to build a like a you're acting on a graph with three vertices. Well, it could be rep A3, it could be rep S3, it could be the direct sum of the trivial representation three times. There's just different ways to build these things that make it very challenging to kind of classify. But for PSU2, if fib acts on a graph with four vertices, it's the module category is fib plus fib. All right, there's nothing
Hmm.
else that can happen.
I see. Yeah, that makes sense. And I could you also maybe explain to me in a more intuitive way, maybe what these adjectives like separable. So when I first heard separable, I thought this meant that I thought this seemed like a condition that we need to act in a well-behaved way on the vertices. But
Where did I?
but it seems
So this V1 space
yes.
is always so by like just generic category theory, this V1 space will always be an algebra because it's the image of one, the unit in the tensor category or the
Yes.
fusion category, which the unit has has an algebra structure already on it. Um,
Okay, maybe we have to begin with an explanation of what based means. When I look at the quiver, what distinguishes a based action from a non-based action on
so
a quiver,
you should think of this as based action is it's not necessarily associated to just the quiver, it's just the for general fusion category actions and algebras.
right?
I am like assigning these subspaces to like so a fusion category action generally is just one of these.
Uh-huh.
But I'm picking out some subspace for all of these spaces, such that that subspace kind of is preserved by the morphisms. And so,
Okay, so I'm kind
kind
of
of
picking
implies
some kind
that
of orbits or something, or
it's like the way that I think about it is that like if you had a group action or like Hopf algebra action, you have some notion of fixed points.
hmm.
In a fusion category action, there's really no intrinsic no motion of fixed points. It doesn't really make sense. Like what does that even like? Doesn't make sense.
Right.
But this kind of gives you like some fixed point of the action. Like these things are somehow not moved by the
Uh-huh.
action. Um,
And so a based action is something that has certain
yeah, and so the reason why I
fixed
define this is my kind of my
points.
original motivation here was to kind of connect, there's it's well known that if you have a group action, you produce a vec G action. But what
Hmm.
vec G actions actually are group actions? And it's
Hmm.
these based actions over this specific functor here.
Hmm.
And so was the original motivation. And then it kind of turns out that these tools are very like somehow this idea is kind of works very well for the path algebra just because the path algebra has this like very canonical base of like these idempotent these sets of orthogonal idempotents that correspond to the vertices.
Hmm. So okay, by this theorem, it's not possible to come up with a group action that is not based. But if I
Yeah, so basically
but
all group actions will give you if you had a group action on the path algebra, you would create a separable base action of vec G on the path algebra.
Right. But if I take a fusion category and it can a fusion category act in a non-based way?
I mean, yes, right? So this is extra structure I'm putting on my, like if we like just in the literature, like the way people define this normally is if you have a fusion category action, it's just defined to be a monodal functor from C into BIM A. You can totally
Right.
have this not, you totally can study this without having putting extra structure on there. Like there's a paper by my advisor and some people who study like inductive limits of take the inductive limit of a C-star algebra and you can study actions of fusion categories on this inductive limit algebra. They don't talk
It
about
does
base
not
actions
make any
whatsoever.
sense to me, but
Yeah, me neither. I don't know C-star algebras and inductive limits, but like there's the point is that like they have some infinite dimensional algebra and they
right.
are forget the fact that it's a C-star algebra. They are acting fusion categories on that algebra in this exact way.
Uh-huh.
They don't put this extra bit of structure.
Okay, so this just means I take my algebra and I change the multiplication by this bimodule formula essentially, right? Like I change multiplication from one side through some automorphism or some action of something, right?
Sorry, when you repeat that, I missed. It
So
jumped.
the a general action is just, I mean, I change the multiplication of my algebra slightly by something, right? By
Yeah, so a
multiplying it
general
with
action, you can
something.
think of assigning each element in the fusion category with some bimodule,
Right.
such that like it's compatible with tensor products. So like
Right.
it's kind of like it's you can think of these as like generalizing like a monoid homomorphism, but like you send the unit in the fusion category to the algebra, and then every x gets associated with some bimodule, such that all the tensor producting is kind of compatible.
Right.
And what I'm doing is I'm putting extra structure on this to kind of
Uh-huh.
capture when our, you know, you know, this base action is a fusion category action, but I'm also throwing
Yes.
in a little bit more data. And that data is kind of trying to capture when do group actions give you fusion category actions and when do fusion category actions give you group actions. Or if you understand semi-simple Hopf algebras, that as well.
I wouldn't say I do very much, but
This is,
I think
this,
it's starting to make sense. You're just, yeah, so you're trying to stay kind of close to group
yes, it's like
actions.
trying to somehow pick out what about fusion category actions kind of gives you group actions and then study those kinds of actions.
Right. All right, thanks.
Yep.
Great. Do you have any more questions? Okay. Well, thank you again, Alex.
Yeah, it
That
was
was
Thank you
great.
very much.
Thanks.